is Vamsi, PhD scholar, under the supervision of Dr. Ramakrishna Gorthi. So, the immediate topic in this next session is on prerequisite mathematics basics. This session helps you to stay engaged in the further sessions during this workshop period. It gives me a great joy to introduce and invite our next speaker today, Dr. Subrahmanyam Gorthi. He is working as an assistant professor in the electrical engineering department of IIT Tirupati. Before joining IIT Tirupati, Dr. Gorthi worked as a chief engineering in the Health and Medical Equipment division of Samsung R&D Institute in Bangalore, India. He was a postdoctoral research fellow at Harvard Medical School and Boston Children's Hospital. He did his PhD in medical image processing at EPFL, Switzerland. He did his master's in computational science at IISc Bangalore, India. Dr. Gorthi's current research areas include medical imaging, image processing, computer vision, and signal processing. I cordially request Dr. Subrahmanyam Gorthi to take this session forward.
So, good morning all of you. I once again welcome you all on behalf of IIT Tirupati for this workshop, and we had just a switch of the math basics one, so I will now take, and our other colleagues will take. The next session will be swapped. Okay. So, what I thought is, since there is a varied audience starting from faculty and some who are already working in machine learning, and some who would like to learn machine learning, and also different backgrounds, the way I will do this is, maybe for the first half an hour I will kind of try to see in general about machine learning, but that also will eventually lead to why we really need such a strong math basics in machine learning. So, that is what we will do for maybe first half an hour or so, and then for the rest 1 hour we will see some details of maths that would be required, particularly about vectors, matrices, or in linear algebra in general. Okay, that is how this is scheduled. Please be interactive, always feel free to interrupt me anytime. Okay, so keep it interactive session. Right. So, you might be hearing lot of buzzwords saying statistics, usually the buzzword earlier, then machine learning, artificial intelligence, deep learning, okay, and many something relevant to that you could still say as data science. You would hear these words, but how distinctly are they different? If you see it, this is something I found nice, is you typically, the backbone or the skeleton is statistics, okay, and you put a frame around it, and you would say, when you are hiring somebody, you would say that I would require somebody who is working in machine learning, all he does is statistics. That's how you ask for. And when you are asking, you are writing proposals and all, more generic word is artificial intelligence, so you start using the words like artificial intelligence, and yeah, now we are calling learning systems and learning methods, okay, for this workshop. But still, all of them, the skeleton would remain more or less the same. Okay, so anyway, you would see the great possibilities and the potentials and already demonstrated usages of machine learning and deep learning systems in general, learning methods over these 3 years. But what I want to also do here in this initial presentation is to put some cautionary posts here about machine learning, deep learning, and how easy or how difficult it is, and how powerful it is, or what is required to master it. So, let us also see some cautionary things here. By the way, many of the slides that I will be using here are a very nice talk by Professor Jayant Haritsa from IISc Bangalore Computer Science Department, a great professor, and I hope this link still works, so please try it after I share with you, and if possible do watch it. Okay, this is a very nice talk. Right. So, let us have this again, that talk was earlier in the context of data science in general, but again, these days data science, machine learning, these all have very close relation. So, still those things would be applicable here. Earlier days, if you look at it, whatever conclusions have been drawn, whatever inferences have been made, they are all based on empirical data. That means you mix couple of chemicals, you see something has happened, then you will say that you mix this with this and you will get the other one. So that is how the research has been driven. Then you would see theoretically to explain the data. Okay, for example, the gravitational law, y equal to mg, you see that, you realize that, and then you tell me the mass, not y equal to mg, after y equal to mx I am saying y equal to mg, w equal to mg, okay, the weight is there. So you would say, now you give any mass, you could say how much it weighs, or you can say if you go to Mars how much it weighs, everything you could say, that is theoretical. Then comes, still these are all prevalent, it is just that the priorities would have changed. There were times when simulations, you would be doing some, you want to understand how certain fluid flow would evolve, you would simulate things using finite element analysis or something else, and you would see what is going to happen there with those things. But now the trend has reversed. Earlier it is through a model you are doing, but now you have data and from that you need to figure out the model. Okay, so it is nicely kept. As earlier there is some driver, now this data, the roles have somewhat exchanged apparently. So that is how it looks like right now. Okay, so this is again one of the things I liked is they have conducted a survey looking at, I want to master machine learning, lot of jobs are there. For those who are faculty, they are forced to teach it now to the students, and they all should get placed in wonderful places. So how do you master machine learning, deep learning, learning methods, learning systems and everything. Okay, so they have conducted some, the details will be there, some data science. They talked about data science. Okay, that, as I said, if they have Python, you still have this PyTorch and all these things which you would be using. So what should I do if I have to master machine learning? So people would say learn Python. Then data science is there. Then there are things like Tableau. Some of you might be already knowing that. And then there is some integrated environment where you have to code. So that RStudio, for example, for that something else will be there here. Okay, and then of course big data, Hadoop. So this is 44% of people, they said that if you want to master machine learning, Python is the most important thing. Okay, that is what they come to the conclusion. And 51% said you should learn this software Tableau, and then these followed. Okay, but and then you will also see other things also. Now you would see a lot of places, we will offer course 3 months, we will make you an expert in data science or machine learning or deep learning. Okay, and what else, we will also craft your CV such that it is just late on your part to submit your CV and you will get job there. Okay, so this is how it is there. And these they call it as boot camp outcomes are this and 3 months. Okay, so please don't expect any of these things from this 3-day workshop. If you have carefully seen it, we were careful in that aspect. You see what is the expected outcome. Did any one of you remember what was the expected outcome of this workshop? Impetus or motivation to study learning systems and methods. Okay, so please be careful if you have not read that, and if you feel that you wasted 1500 rupees or whatever you are paying and all these things, we are sorry for that, but there is a disclaimer there. Okay, our outcome is the disclaimer, but nevertheless our expected outcome is that you will get some direction in which to pursue. Okay, and some impetus or motivation to pursue. Okay, this is the expected outcome of this 3 days workshop. So I thought in that way this is relevant, and I kept this here. Okay, so do you know the name of a movie ABCD? What was the abbreviation? Anybody know that expansion of that? Anybody can dance. So he has tasked anybody can do data science. Okay, now forget about your degree. You join in our group. Okay, we will charge you 1 lakh 3 months. You do those courses. You will be all right. You can get a very good, fantastic job. So anybody can do data science. You means this is ABCD is still looking good, so I kept it. Otherwise, you put anybody can do learning systems or whatever you want. You can keep it there. And then another thing you would keep on listening to is data is the new oil. Okay, you burn that oil and you will get the light, and in that light you earn or whatever you want to do, and new quantum mechanics that brought in all those things. But there he says in data science people forget that the most important thing is not the data but the science. What does the data science word mean? Can you give a little more explanation of what perhaps, why do they call it as data science? There is no science in data, correct? Science is different, data is different. Why do they call it as data science? It is still relevant to learning systems, okay? Because you are learning from data. Why do you think they call it as data science? What is so scientific? Where is the science in it? No, science is from the nature. If you are doing something, you should call it. This is scientific approach to analyze the data. That is how you could make an interpretation to that word, but again it is arguable whether data science is the right word or not, but anyway we are not going into that. But here what it means is you use scientific approaches to learn the data. So you could that way at a very higher level, roughly you could see data science, learning systems and all those things in a way synonymous. Okay. So this requires understanding of physical mathematical principles of data domain, not just programming environments. Okay. This is not enough. If you learn PyTorch, very good, Hadoop, excellent, and all those things is fine, some environment, some programming is good, but that is not enough. There is science, you don't forget about science and don't just carried away by programming. It by no means belittles the role of all these things. This is indeed required, but this is equally important, I should say more important than the other one, if not more, at least give an equal priority there. Okay. So this is again from a Nobel laureate quote, if you torture the data long enough, it will confess to anything. You bring lot of data, okay, you overfit the system, train it, it is not enough, bring one more million data set, do it, you might be getting something, but when it comes to testing, God knows what will happen. But this is important, okay, if you are not getting results from your machine learning algorithm, don't ask your poor supervisor to provide him 1 million data sets more and couple of more workstations, okay, you should look into whether can you figure out some good features there or some other approach can be done, that also. Yeah. So give some benefit of doubt there. If you are not getting it, also look into the domain problem there. Okay. So this is another nice example. This is published in Nature 2004, one paper got published on linear regression. Here your x-axis is the year, your y-axis here is the time taken for them to complete a running race, to finish a running race. Okay. So these points, men in blue here, okay, women in red here. So this is what the time they have taken to complete. The first person who has finished the race first has taken this much time. Over the years, this is what happened. Now you know linear regression. By the end of this workshop, you will become masters of linear regression, and somebody asks you to predict what would be the time taken in 2150 to finish this race, and who will do well, is it men or women? Okay. So this is how you could do all your linear regression. If you don't know it, it is just, to make it very simple, you fit an approximate line which is very close to all those points. So can you draw inferences from this? Maybe the picture is not very at a high zoom, but still, can you please make out something out of this? At least what will happen in 2150 for who will be doing well? Is it men or women? Means I have no discrimination here, please don't take it in the other one, just for the statistics we are looking at it. So who would finish it first? Women would finish first. But see the data that we have till here, every time they are running fast here, but what happened here is the slope is more. Who told us that it fits into a linear regression? Nobody told us, right? But if you assume already that linear regression is the best thing, okay, means it is good, whoever wins, but that is not the way you should look at it here. Linear regression might not work all the times. Okay, even worse, there is something even worse than that. Can you predict what will happen in 2000? This has been 150, take 2200, and can you tell me how much time either men or women will take to finish the running race? 5 seconds, no. It's a linear thing. They will finish before the race started because it can go to minus 20 seconds. So no need of any race at all. Okay. That is very clear, mathematically hence proved. We can write it there. You cannot contradict this. But you don't worry about looking at any other features, you just looking at slopes and assuming that linear regression works. This is the mess that could create. Okay. So on one side, first point wanted to drive is just knowing some software tools and becoming an expert in 3 months, 2 months or whatever. There is no magic wand with them that will convert you into a different human being. Second point, it is not just even if you are fitting something, you should have an intuition for it and it should correlate with your intuition. These things being in place, there is no denial of the fact that people are after machine learning and deep learning for a reason. They are doing some tasks at a very mass scale at such a higher efficiencies, and there is a leapfrog jump there, the efficiencies achieved. So there is no undermining of that fact, but these two, the domain knowledge cannot be replaced with your programming skills. Similarly, the mathematical knowledge. Okay, linear regression knowing alone is not enough, but that mathematical understanding is indeed the backbone of all these methods. Okay, so again, one more means you all came for learning and hearing good things about learning systems and methods, but it's, as I said, these are only the cautionary things we will do for all the rest of the 3 days. We will be doing it. Okay, say since some of you are already working on it, you would see that you don't earlier what you do, you extract some features, feed those features to your network, it makes some sense out of that, and then it tells you some problems are, for example, classification. Okay, classifying whether that belongs to so and so object or the other object, that people will be doing. At least in the beginning days we used to feed it some features, that is handcrafted features you are giving them. Now this also has a limit, there is a limit beyond which you cannot do for all applications that too. When we are not having a full understanding of the domain knowledge, it is not possible. So what you could do is, now you have great networks that even extract features for you. It will also tell you if you want to separate this from that, this is the feature you need to look at. Just give me some training data which says, for example, the cats versus dogs. Okay, initially you have to say look at its ears, look at its legs and some texture on its body, height, something else, maybe its mouth, something you have to give. Now they are in such a state that you will get a very good accuracies, even just you feed some millions of images saying these are images of cats, these are images of dogs, I don't know anything, you figure it out and give me the answer. It can do, but at the same time one should be aware, particularly in those applications which are very significant, whether it is able to do the task, is it because of correlation or causation. You all know causation, cause and effect, the law of, so there is one reason for this and that result, because of that something has happened. Okay, correlation is there is some relation. Okay, say for example, let us take a contemporary example, there was COVID. So during COVID nobody is coming out, most of them if not are coming very occasionally outside. So traffic is less, because of that accidents became less, everybody is at home, where will the thieves will come? So they have to close their business. So there were less accidents, there were less thefts happening. Now one way, if you give it to a deep learning network to figure out when will be more thefts, if you ask it and feed this data, what it does is, when there is COVID, COVID is the cause of lessening the thefts, COVID is the cause of So if there is no COVID, there will be more deaths. That is the what you will get the inference out of it due to accidents. Is this cause or are they correlated? What do you think? They are correlated. It is not because COVID is there, they got introspect and they felt that no, I should not do any more thefts, I don't know when I will die. It's not that way, because of the COVID people are not moving out, right? Because there are less people, there are less accidents. So for example, you might consider some application where in a medical imaging, let's say, you are doing for example, whether in a lung there is a cancer is there or not, in the lungs you have given it X-rays. Assume that one set is for is those images which have cancer and other doesn't have the cancer. Okay. If you do not look into this, there could be something that they all might be coming from one center and this might be coming from other center, and there could be something else which is not exactly related to it, but it still might be giving you the good results. But unless you see the features, for example, one center might have acquired all from posterior to anterior, they are making you are standing like this, and it is that is, for example, those were the images acquired in an emergency ward. Obviously there are more chances that it will have cancerous cases. Another is done in the regular ward. If you don't look at it, pay attention that in which direction it is acquired, and if you are simply giving it learn that features, do it the job for me and give the output, it might be doing just because of the variations in the way of acquisition, not because actually it is extracting the features of a particular abnormality. So some interpretation of the results is required. So the way you should also, we should see whether what is it is exactly looking at and how it is doing the job. Now, the example there it was given is when it is a hot day, people going out, this is a European example, so they could have sunburns there, and anyway in Tirupati we always have it, and there is no difference, right? There is always a sunburn, and people would be eating ice creams. So if you say, if you eat ice creams you will have sunburns, you take the list of all people who have eaten ice creams, then there will be of course sunburns because they are coming out and eating ice cream also. So this is correlation. This is because of sun having sunburn is a causation, and because of that eating being very hot day eating ice cream is a causation. But if you are looking at these two, it is a correlation. So one has to look at the subtleties of that and see what exact you need to make an interpretation of your learning system. Hope the point is clear, the distinction between correlation and causation. Okay. So as I said, the backbone of all these things is indeed mathematics. So it's in a way statistics put in a frame as was shown in a cartoon, not too far from the reality. So you do indeed require a good understanding of random variables, linear algebra, vector calculus, multivariable calculus is what I mean by that. So all these things are indeed required, okay, and don't rush and end up as a blind practitioner of ML. Don't say that if I know it I would not have come to the workshop. It is giving you here, and that's why what we all do here is we will also give you some pointers to look at. You could also of course you could look at, and some of you might be already knowing that. So it is to bring some awareness and knowing what all references you could perhaps go through, and don't expect to become a superstar overnight in machine learning, okay, please don't expect that. And ML is a, as I also mentioned, ML is a support but not a substitute to domain knowledge. This also you have to keep in mind. And yeah, maybe these two slides I will come a little later. So again I am also carrying my textbooks to my class also, not because I am getting any commission from these textbook guys, okay. So buy some good books, have them with you, and still that habit helps you to go in details, just not you get some question and then you Google it and you get an answer for it, but follow some properly like for any other subject that you are doing earlier, okay. We all have how many of us, when it comes to the classical subjects, for example, since many from ECA background are there, if it is DSP you will look at Oppenheim and Scheffer, if it is some other subject you study. But when I ask you what is the book that you are following for machine learning, you will say I am following some course, Okay, somebody I met here and he has told me some references, I am following it. But it is indeed to have a very solid background, and this you do require to study it thoroughly. Some books I am giving here, by no means this is, there are quite a few good books, these are some of them. This is what the last semester which recently concluded, this is the one I followed for most part of my course, pattern recognition. This is by Theodoridus, Greek authors. This book is nice, okay. And this again, this is also a very nice book. I could not bring all the books, I can't, just to show that this is also nice. I will keep, if you want to just skim through the contents, you can go through that. This is also again a very good book. By the way, just there are quite a few courses. I think anyway I haven't kept here the courses which were already many of the people are knowing. For example, Andrew Ng's course, do them properly. It means again, along with that, follow a textbook. There is by him an introductory course on machine learning, introductory course on deep learning. These two things are there. And there are courses of Mitesh Kapra's, Dr. Mitesh Kapra from IIT Madras. You can please make a note of it. His course is also available on NPTEL. That's also a very good course on machine learning and deep learning stuff. Okay, so please go through such courses well. Okay, and then I'll share these things also if possible. So there is one course, there is a course here, machine learning for image processing course, which is a core course for MTech students. I happened to offer this last semester, and before that Dr. Ramakrishna was offering this course. So both the courses, all the video lectures are available online, and even the material including assignments that were given, and final exam paper is also there except the solutions. You could see that there. So these are some references I am giving here. Again, math basics in 3 hours is, again, we can hardly cover it. It can go on and on. So what I will do here is, me and my colleagues will give you some glimpses of it and some pointers to it. So after that, you follow there is no, it's not like in 1 hour you can learn all linear algebra that is required, 1 hour in random variables and all. It can give you some pointers there. So look at it that way. But if you go to those lectures, for example, Dr. Ramakrishna's course, you will see he separated the math part initially, and then you will see the rest. So you might go through them, and here also it is interleaved, you will see the both. Okay. The left hand side is a benign tumor, and this a malignant tumor. What is the characteristic that you would see one distinguishing from the other? What is it that you would see there? Color. So which is bright? A very trivial question, just that I want to hear from your side also. Yeah, I assume that this is benign. Benign means there is a tumor but not dangerous. Okay, it doesn't multiply. This is malignant. So which is bright? Is it? That is bright. Okay, then it was not a trivial question. Okay, you see more light there. Okay, that is a bright one. So the question now is, how can you do this automatically? One way you could do is, for example, you could take the mean intensity value of the image and also look at the variance of intensities in that image. And now assume that one of these circles here is representing one class and the other circles are representing the other class. So given that this is bright and we are assuming this is benign tumor, you could perhaps, the circles are belonging to a class here and the other one here. So if you have a data set, what you would do then, this problem is referred to as a classification problem. That means, is that a benign tumor or is it a malignant tumor? You have to say that. Now you are able to say it by looking at mean and variance. You are given that. So what you will do now, here you have taken the mean intensity value of your image, you have taken, sigma is standard deviation in that case. So then you have seen one class, all classes here, zeros, I have a training data, it cannot learn on its own, you should feed it the relevant data. You have given that data, all the circles I am showing here are let us say benign, maybe some cross here, these are the malignant. So, now what will happen, this is what you get from training data. What we mean by training data? We know what is the outcome, expected outcome of this, that is what we refer to as training data. Now, a new image has come, okay, that is falling somewhere here, its mean and standard deviation. Then what will you do? Will you say that to benign or malignant now? Malignant, because you assume you have seen some separation here, okay. This is what is a classification problem, and this is what you expect your machine learning algorithm to do that. So, again if you look at it, essentially in all the machine learning thing, you are figuring out a unique signature of each of the class. A unique signature means you have to somehow characterize that. One simple way to characterize is you take each pixel intensity value, you can put it as a vector and see something is happening. It is a little higher level than that. Those features, for example, if your image is 100 by 100, okay, you have 10,000 features, we call them as features. Feature is something, what is his feature? He is tall, okay, he is thin, so on and so forth. These are the features. Similarly, there initially you could have taken every pixel intensity, that means every pixel intensity is a feature, so you have 10,000 features there. Now instead you have taken here another way to do that is you have extracted some features there, okay. One is like taking the whole image and looking at each pixel value, rather now you are looking at what is the mean intensity there, how many features are there now? 2 features are there, you refer to it as a feature vector now, okay. That is why now vectors are coming in now. So, that is how, so what do you mean? So, you may also call it as the pattern also. Each one has a unique signature, that is what you want to extract and do it. A simple way, if you are looking from an image, you have seen some examples of audio earlier, okay, with respect to time you look at it. In an image now you have it in the 2-dimensional thing, you could take every pixel value and do the analysis, or otherwise you extract something. So, when it comes to deep learning, one way of distinguishing deep learning versus machine learning is you do not even know what features to look for, your algorithm or your architecture is expected to give you the features also based on very coarse things. For example, the coarse thing could be the intensity of each pixel you give it, it extracts some unique signature or it learns the unique signature of each class. Is that clear? Okay. So, yeah, this is what I, just to summarize here, I think, yeah, that is fine. Just to summarize here, as I mentioned, want to alert that this is not a 1 month, 2 month, 3 month business or a 3-day workshop business where you would become a master of it. This is something you put consistent effort, follow it like any other conventional thing, first point. Second point, math is indeed the skeleton around which you can have all the flesh and blood, but without skeleton it does not stand, okay. That is the second point. And third point is domain knowledge, yeah, ML and deep learning do not look at it as a substitute for your domain knowledge, both should be complemented. We will be complementing each other and should go hand in hand. At the end you should have some interpretation should be possible. That these are the 3 key points wanted to convey from this slides, hope that is clear. If so, we will see some math also. As I said, I will go through very few things, that too I will take some machine learning problem now and I will show you what kind of vectors and matrices operations you would require there. That is what I will do for the rest 40-50 minutes or so. Can I, any question? I will just give a pause here. Any of you have any queries or thoughts to share about that, or disappointment to share about? Not disappointed? Okay, good. So, yeah, maybe if this board goes up, I can use the full one, otherwise also it is okay. Now, you want to solve this problem. What kind of things would you require for achieving this? It is a very trivial case, for drawing it is easier, so we have taken mean and variance. That need not be only the case. you might look at, for example, circularity of it, the length means for a different application, the length geometrical properties of it might help you. So assume that you have some 10 features, even of course with even simple 2 things we can do, but let's assume that you are given an image and now you extract features of it, and your feature is not just one value here. So let's call that now, let's call it as one of the for one sample or one image you have given, let's have these features x1, x2, x3, let's say a d dimensional d features are there. In a very simple case, if you have a image of size 100 by 100, one simple thing you could do is concatenate everything, put it into, so you have 10,000 things, so your d could be 10,000 there. Okay. So now you need to deal with these things. The convenient way you deal with them is what representation? Vector representation is what you would use here. Okay. Now anyway, still for drawing purpose, I will just restrict to 2-dimensional one so that I can conveniently draw here. Assume that I am looking at only just like the example there, I am simply looking at mean and variance. Okay, these are my 2 features I am looking at. What happened for me now is, for one thing I got points here, and another class I got some other points. This is belonging to class A and class B. This is class A, and another class I am representing here as class B. Okay. This is what I acquired from given training data. Now what happened? There a new image has come, you have developed now your algorithm, you have to figure out to which class this new one belongs. So assume that my new sample has come here. Okay, this star is the new sample that has come here. Tell me some ways, okay, just intuitively, what do you think, how can you figure out whether this belongs to this class or this class? How do you assess that when you look at it? Whatever approaches you could think of, please tell. How can you assess to which class it belongs? Very good. So which is close to it, you assign to that class. You see probably this is closer here, you put it into this class B, right? How do you know which is near now? Mathematically you have to solve it now. Very good. Say for example now, assume that this x bar could be the new sample that has come for you, and let's say there is one more sample y bar which is again, make a note here, all of them will be of same dimensions. Okay, just I am drawing here 2, otherwise this are there. Now what is the kind of distance that you could compute here? Euclidean distances. How will you see here? This is the distance typically you look at, right? And this is the another distance that you could look at here. This is nothing but the Euclidean distance. Now with that, now suppose x bar and y bar are there. Now let us translate this into now the vectors part, into the mathematical terms. How do you compute the Euclidean distance of 2 vectors here? So first write the expression for this. So let's say, yeah, how can it, first write, tell me the expression, later we will put into some terminology there. So how do you compute the Euclidean distance now? Okay, can I square the Euclidean distance also? Will it still be okay? Because anyway I will be comparing the relative magnitudes, right? I want to just get rid of that square root also. So how can I write it now? x1 minus y1 whole square, x2, right, whole square. So for example, summation I is varying from 1 to d. Okay. This is one way. I could compute it. Now, how is it represented in terms of this thing? So, I need to take, can you do you know L2 norm? Have you heard about that? Okay, can you express that into L2 norm of something? L2 norm, you know, that's Euclidean distance in a way is a special case of that. So, this is how you represent that. So, you take x bar minus y bar. How do you take a difference of two vectors? Simply subtract the corresponding elements. So, that will give you, what will be the elements of that? x1 minus y1, x2 minus y2, so on, xd minus yd. Now, when you say the L2 norm, that will be taking square of all those things, but I just had a square here also just to avoid anyway. Finally, what was the idea? You just assign it to that, you compute the distances to each feature here. This is called as nearest neighbor classifier. You compute the distance to all of them, whichever has the least distance, you assign it to that class. Okay? And again, instead of L2 norm, there is another thing also people would look at it. Any idea? L2 norm, not that one. You can make even a guess. L1 norm. They will take sum of absolute distances because you could avoid it has its own advantages and pros and cons as well. But to put it simply, that is like what you would do is here absolute value of x1 minus y1 plus x2 minus y2, you just take absolute values of each and sum it up there. Okay, that you would refer to as x bar minus y bar, the L1 norm there. That is one way to do this. Any other way of classifying you could think of? Very good. How do you compute the similarity measure? With what is it the similarity we should look at it? Right. So, now you make again we will use this today for an example. See, if two features are very close, that means what could potentially happen is both are in the same orientation. Then they are, why I am saying orientation? Because that will give you the proportion of these two features, correct? x1 and x2, the proportion of these two features it will give you. So, the way it can be done is, let us first write it for, let us look at here. Assume that, see I have x1, y1, this is a vector, right? This is a vector. I am just restricting it to a two-dimensional vector right now, okay? Now, so that I could draw here, there are some vectors like this. What I also did here is to make this magnitude to be 1. How can I make the magnitude of a vector 1? That is all. You just divide it by square root of that, you can make it normalized. Now, is there any way now you could say, let us say, which is closest to this thing? I have vector, let us say x1 bar, x2 bar, x3 bar, x4 bar, okay. I would like to see which is the closest or most similar to this x1 bar, okay. If you, these are all unit vectors by the way. How is there any way that I could quantify that? Very good. By taking the dot product, what will happen with the dot product? Suppose I have a bar, b bar, two vectors, magnitude of a, magnitude of b, right, cosine of angle between a bar and b bar, correct. So, it is, in other words, it is nothing but the projection of one onto the other, right. So, anyway we ensured that a and b magnitudes are 1 by saying that these are the unit vectors, features you can always normalize there. Once you ensure that, the closer they are, right, then the most similar they are. So it is again similar to what has been discussed in the previous talk by Ramakrishna sir, where you have seen this is, you are looking at the correlation of that with the other. So let us say now, if I haven't normalized here, what I could do here is x bar, so dot product of, so how should I write dot product? Let us say, let me write it here, and norm of x bar and norm of y bar. Okay, if I do not keep anything, it means usually the L2 norm. Okay, that, so I am making them this, and I am taking x bar, y bar. Okay, so how can you write this in terms of, how can you find out this x bar, y bar cross product here, sorry, dot product here? Given x1, x2, x3, how do you calculate that now? Very good. So if you take it here, the way you do it is x1 y1 plus x2 y2 plus so on plus xd yd, you have to calculate. That means, what is the dimensionality of this? What is the dimensionality of it? D cross 1. What is the dimensionality? Of course, this is also D cross 1. What is the resultant? Once you have two vectors here in n-dimensional space, once you project it onto the other one, what is the dimensionality of the resulting value? When the vectors are of same size, of course, otherwise you won't do the inner product or dot product. What will be the resultant value? Will it be a vector or a scalar? It's a simple scalar. So how do you get that now? So, this is what you need to get it. That means you need to do x bar transpose y bar, right? X bar transpose is 1 cross d here, then you multiply, so 1 cross d, d cross 1, the whole this column, sorry, this row you multiply with column, and some respective elements are multiplied and summed up, x bar transpose y bar. Okay, can you mention it in some other way also? I don't want to take transpose for x, I want to take only, I am okay with taking it for y. Can I write it as x bar into y bar transpose or something else, something like that? So I want to take transpose to y only, what should I do? Well, that's all. Okay, just to ensure, is my talk good enough to induce some sleep? I am just asking this. Okay, y bar transpose times x bar. Okay, is that clear? So anyway, since we have seen, this is also referred to as inner product. There is something else. What is that? Outer product. That is what we have written earlier. So where you take d cross 1 and then 1 cross d, so where you take x times y transpose. Anyway, we will not go into that detail right now, but that's what it is. That is called as outer product or cross product. This is the inner product, and inner product with this normalization is also referred to as normalized cross correlation. Means those who are from ECE background knows this, right? Normalized cross correlation, this is equivalent to, that will give you the similarities. What would be the range of these values? Always 0 to 1, or should I put something there? -1 to 1 or 0 to 1? So typically in all your, if you are already programming, most of the times it is between 0 to 1, provided it all has x1, all these values are positive. Look at here what you are doing. You are multiplying, this is what you are doing. If all your values are positive, okay, it cannot go negative, but if your features can have negative values, then it goes to -1 to +1. Okay, you all know it, inversely correlated, -1, 0 no correlation, 1 maximum correlation. That is what you would see there. Of course, that if you just write this, this is this is normalized cross correlation. If you just look at it, that is the cross correlation. Fine. So what you could do here, first method, you have looked at L2 norm, one way to do it, nearest neighborhood is how you are doing. Second, you have used L1. Third, what you could do, how similar is this to others, right? So you project this onto every other one. Of course, these are normalized vectors. So when I normalize it, you just look at this vector something like this because they are normalized. Look at that, and which is very close. Obviously, here itself there is another sample was there from training data. Of course, that will be 1, is it not? Because you are projecting this onto the same thing, it's a unit vector, you will get the correlation is maximum. Those are 3 things that you have looked at. Okay. Hope it is. Any questions here? Is that clear? If so, we will move on to, I think we have spent some time now on classification. At least we have seen 3. Anyway, tomorrow we will see more methods for doing this classification, where you would be using neural networks to do this classification. By neural networks, for example, if you know that these are linearly separable, how could you find out a line here that separates them? That is the first part you will see. Suppose they are non-linearly separable, then you would use more neurons there. That is what is in store for tomorrow, but for now we will stop the classification here. If you, again I will give you a pause here. Any questions? I will talk about is, again what I will do in similar lines, I will tell you the problem, and hope you have seen here how vector algebra vector operations are essential to you, cross product, dot product, L1 norms, L2 norms and all these things. Okay. In similar lines we will see what is the math required for that. Have you heard about regression, linear regression problem? Some of you I am sure would have heard about that. So we will have some look into this linear regression problem. What is this all about? Can any of you share your thoughts about linear regression? Fitting a straight line? Yeah, straight line you could say, as long as these are only one input and the output you are looking at, and then it is linear, it is fine, or a linear hyperplane in a way, and then figuring out what's the value is. Okay. I am sure some of you would have done the popular courses, all these courses. So by any chance any of you remember the any example for linear regression that will be given?
Number of house price.
Excellent, very good. I am glad to hear that. So the linear typical example, I think it's again from Andrew Ng's, Professor Andrew Ng's one. That's the conventional classical example that they give. So number of bedrooms in a house, let's say. Okay, I don't remember. I will add my own imagination here and add these things. Don't take them too seriously. Locality. Okay, the square feet of that that it is occupying. For example, swimming pool. Okay, we cannot afford it in Tirupati, so I will not write that. I will just put localities of Yerpedu and Tirupati. Now we are in Yerpedu, so we will keep both. Okay, so based on that, what could be the cost? Okay, what could be the cost of the apartment based on this, if you want to say it? This cost can take any value here, from any linear, any real value it can take. It's not, see, compare it with the earlier problem that we have looked at. It is either that class or this class. It's a kind of binary in a way. If you are just looking at two classes, it can take only discrete values. Here the cost can take any value. Okay. Now let us even further simplify this problem. Okay, this is when you have a linear hyperplane or whatever you call it. In a higher dimensional space you have it. Let's only see square feet and cost, for example. Okay, now you can pose this problem like this now. For example, I am drawing here how much is the square feet of that apartment and what is the cost of that. Okay, assume that it started from 100 square feet. I don't know whether that makes sense or not. Still keep it. 5,000 square feet. Okay, and then you know the costs here, some you know from your training data what those costs are, right. Now somebody has come in that somewhere in between, it is not there, let us say 1000 to 2000 in between, nothing you do not have in your training data. People were asking you about what will be the cost here for 1500 square feet. How will you do that? How do you solve that? We have many disciples of Andrew Ng here, at least few, good, glad to see that. You fit a line, unfortunately it does not fit so nicely to all those points, okay. So I will draw a line and then put points around it, it is easier for me to do that, okay. I will fit an approximate line to this, and then what I will do, now I might require something in between here. Now I know from this, for example, I know this slope now here, slope and intercept I would know once I fit this line, okay. Now I know this x value, how many square feet, from that I could figure out what is the cost of it. Shall we solve this problem now just for 2D case, okay. So how do you think we can solve this problem now? This is simple, fitting your data, assuming again here it's there is a linear relation, as I cautioned earlier, linear regression should be used with discretion, otherwise you might finish your running race in -5 seconds as we have seen earlier, okay. So here the assumption is it fits well here, okay. Let us come back. So how do you do that? So let me pose it slightly differently. You have points x1 y1, x2 y2, let us say I have points xn to yn, these are the points I have, okay. I need to find a line that best fits these things. So if it is a just a 2-dimensional case, I could write it as w1 x1 plus w0 is equal to, so if I call it as y, for example, y, can I write something like this? So yeah, this point is xi, yi I write, okay. w1 xi, y equal to mx plus c, just that I have something else in my mind and that is why I am using w instead of your favorite y equal to mx plus c, no, nothing changing here. w1 xi plus w0 equal to yi, this is what I will write, okay. Let us now graduate here itself to higher dimensional space. If it is a linear hyperplane you are fitting in, where you have this instead of this is multiple one is there, xi1 xi2, if I write it, how could I write then? So instead of it is only one dimensional, my input. Now assume that since I committed here with subscript I here, let me write it as, let us say I1, xi2, xi3 and so on, this is my xi bar, okay. Then can you think of how this equation should look like if I go to higher dimensional space? For example, maybe we will take the next step rather than jumping too high. Suppose instead of 1 I have 2 xi1 xi2, okay. I am using locality also here, locality and square feet for cost. So how do I write this equation now? W1, let us say xi1 plus w2 xi2 plus w0 equal to, should I have that? I have only, output is only 1, I can still keep yi, that's still a scalar, because at the end of the day I am just predicting one real value, okay, yi, okay. Now we will now move on from earlier vectors to matrices now. Can you write it in a matrix form? How do you write that? I want it Ax equal to b, you all know, right? Again matrices means Ax equal to b, line means y equal to mx plus c. So you tell me now, how do you write it in a matrix form? Is that one equation enough for you? So maybe I will give you a little more things. Let me call this xi bar, let me define that, which is equal to xi1 xi2, okay, and let us say xi n dimensional space or d dimensionals you are using, points are n, each one features are d I am considering, okay. Now along with that w bar I will write as w1, w2 and let us say wd. This is how I am defining two vectors. You are already convenient with vectors. So now you tell me how do you write it in terms of these vectors first. We will come to the matrix a little later, but how do you write this now? W bar transpose x, okay, xi bar, okay, next plus w naught is equal to yi. Should I keep yi bar? No, very good. Now I do not like this being an orphan here. I want to absorb this into some of these vectors here. You have no freedom to define your own vector, okay. So just modify these two vectors such that I have ax equal to b. I do not want ax equal to this variable, because see what is it at the end of the day here you need to find out. Is it x bar, is it yi, is it w naught, is it w bar, what is it that you need to find out at the end of all your mathematical exercise and gymnastics? Yeah, to find out yi, which will give you that, right. Is it only w? What happens to the w naught also? See y equal to mx plus c, if you are doing it, it is not enough to just compute the slope, you need to compute the intercept also, right. So what I want here is, I want all the parameters to be computed into one vector, okay. Simply I want something like ax equal to b, this is something whatever you need to find out here. So can you redefine them to achieve this? Yeah.
Add w0 to
Here, very good.
add 1 to x.
Very good. Now then what?
W transpose x is equal to y.
Excellent. Is everybody with this? Are you able to follow this? This is called as homogenizing these equations, where you just absorb this w naught also here. Although you have d features here, you add one more 1 here. It is not exactly a feature like mean and variance, but this makes your life easier. Later you can simply, all taking derivatives and all these things would be required, this makes that easier. So now, is that small change that we made, is that clear? Good. So what is our equation now? W bar transpose into xi bar is equal to yi bar, okay. Slightly redefine now. This is xi bar means d plus 1, you call it with another name, but I just for the simplicity I say this is d cross 1, it is a matter of using any variable name there, okay. This is where I arrived now. Then yi, very good, right. W because it is only giving you a single value scalar, okay. So how can we solve it using any of these, by converting it to some matrices or something like that? Can we do something here? What do you have here? So let me maybe, for easy to write it to see you clearly in the matrix form, I will still expand this instead of putting it in transpose, okay. So the way I would write it is w1 x1 plus w2 x2 plus so on wd xd is equal to, what I should do, xi1 I should keep, xi2 I should keep, xid, is that fine? Or I'll do this thing, okay. First point I will use subscript 1 there, okay. So how do I write here? W1 x11 plus w2 x12 plus so on. I assume that I have d features, let us say, okay. So this is 1 x1d is equal to y1, okay, x1 y1 I am writing. Is it clear so far what I am writing? Right. will that be always true when I do this linear fit? Will the left hand side and right hand side will always be equal there? No. So what is it that we need to do now? Error. What should we do with that error? We should minimize that error. But this is what you want to achieve, essentially close to that. So minimizing the whole error, that is one way to solve. Perhaps that we will do in tomorrow when we do, for example, using gradient descent based approach, that we will see tomorrow. For now what I will do is, there is one more point, this is what you want to achieve, something close to it. Then there is another point where the second point, see this xi bar, one I have taken, now the second one I am taking. So this is x21 plus w2 x22 plus so on plus wd x2d equal to y2. I have n points. What will be the last one? w1 xn1 w2 n2 plus so on plus w d x n d equal to y n. Very good. Now you put this in the matrix form and tell me now. Some matrix here, okay, some matrix here equal to a matrix here. What is the matrix here? This is easy. Easy ones I will fill, difficult ones you struggle. This is n cross 1 I should get here. Okay. What do you want me to keep here? I want again cross 1, n cross something, because I need to get this one, right? N cross n, n cross n, n cross n or n cross d? Very good. N cross d here, d cross 1. Now you tell me what will come here. W or something else? First you fill the easier one. What is this one? D cross 1. Right. W1, W2, so on, WD. Now you tell me. This into this should give Y1. Okay, this Y1 is there. This is what you should get. Now you tell me here. Very good. X11, X12, X1D. And then the last one is xn1, xn2, and xnd. Okay. This is what you need to solve now. So hope you have realized we moved now from vectors to matrices here. You need to deal with these matrices now. Let's call this as so is it fine or any issue with that? N cross d, d cross 1, n cross 1. Okay. Now what is it that I need to find out now? What is it that we have to solve here? This is what you need to solve for. Okay. So if I write it just for simplicity, Ax equal to b, that is what we have to solve for x, right? Your A is n cross d, d cross 1, that is n cross 1. How do you solve this? This is n cross d, d cross 1, n cross 1. So again matrix, that is why linear algebra matrix, these calculations you should know. So how do you solve this now? X equal to A inverse B. Any problem with that? Right. Rectangular matrix finding inverse is the problem. Make it square. What will you do then? How do you make it square? Change the aspect ratio. How do you make this side, you want something square so that you could find inverse? What will you do then? Right, what will you do?
Multiply with A.
Very good. You multiply on both sides with A transpose here, here also with A transpose. Then what will happen? A transpose means what is its dimensionality here? D cross n. So what is this dimensionality now? Is it a square? Yes, D square is there, so it should be square. A transpose A times x bar is equal to A transpose time B. Now you tell me how you compute x bar.
A transpose A whole inverse into A transpose 2.
That's all. So again you should know the basic properties to find out inverse. We are not discussing, but you please go through the references I have given. You will find out, and even other courses where you see how to find out rank of the matrix. All these things also you should know. So that is all, you should have a sound understanding of that to find the inverse, and that is where even you would learn, for example, singular value decomposition, and all these things also would be required in certain cases to find out the inverse and other things. Okay. So since there are already few people who have done a course something related to linear regression, was this the way you computed, or did you use any other way? So in the conventional thing you would be using some other way to compute your x. So just to fill things here, just to come for the sake of completion here, what is it that you need to do when you have n set of points here is you create this is your A here, from all those points each vector you have it, this is what you will get A, you take the transpose of it, multiply it with A, that is a square matrix, take the inverse of it, multiply it with A transpose, then you have these y values, then you multiply that, and what would be the size of the resulting one? This size is, what is this size? D by D. What is this size? A transpose. What is our A trans is n by D? D by n. What is B size? N cross 1. What is the resulting x bar size? Yeah. So by the way, don't confuse with this x bar. I changed W into x. Okay. Hope you please make that correlation. Otherwise, it is confusing. This x bar is ideally this W what I am talking about. Okay. Should have used another variable, but realized in the last minute. Okay. So this is a D cross 1 thing you are getting. Okay. That's what you will W bar. What you get here is in fact this W bar. Okay. Just switch the names there. So can you now, with just simple MATLAB, if I give you a set of points, can you do that now in any dimensional space? Is that not possible now? You do that, you construct that weight that matrix of features there, A transpose A, you do that, take the inverse of it, A transpose and B, that should give you. Okay. In another way, we are not going into the details of it, but this is also equivalent to least square fit essentially. This will exactly give you the same solution as one of you were telling. This line is fitted such a way that the error here, the distances here, you sum of the square distances, if you minimize that, in that way also if you solve it, you could pose this matrix problem in that way also, and you would realize that is the same equation that you would be getting. So essentially it would give you that solution which minimizes the sum of squared differences. Okay, anyway square you are taking, distance let me call it, negative also does not matter, of this thing. Okay, is that clear? Well, in practice you may use it sometimes and you may not use it sometimes. So those of you who had seen into linear regression, there will be something gradient descent based approaches is one of the other commonly used approach. What do you think would be pros and cons of each of these two? What could be an issue with this? When can you face a problem with this approach? Let us first look at it. When can this become difficult to handle? Which is in higher dimension? Is it are you talking about this x or number of points? Higher dimensions of what? Are you talking about n or d? Right, that is d you are talking about. Very good. when you have a say, consider the same example that we were talking about earlier. You have assume you have an image of size, let's say 1000 by 1000. Then tell me, so this is your size of the image. What I am doing, my whole image I am making it into a vector, okay, and that is my feature I am calling it. So my x1, x2, x3, there are 1 million features, feature vector size is of 1 million then. Then why is there a problem then? What would be the size of this matrix to be inverted? What is the size of this matrix now? Right, this size of this is 1 million by 1 million. Finding out inverse for a matrix which is of size 1 million by 1 million is a problem. Had it been just this case, okay, this is even one, at least take two, mean and variance. The first example of benign tumor and malignant tumor you have taken, there it will be 3 by 3 of course, because we added 1 here. Just pay attention to this. Even in that case it will be 2 cross 2, correct, because to homogenize things we have added feature as 1 here and W0 has been taken care here. In this case it is after all inverting a 2 by 2 matrix here, that is not a problem. But if your feature space is very high, that is when you would see that gradient descent kind of approaches where you would be doing simple multiplications and additions kind of stuff on the each of the element of your vector is easy to handle, and that is when you would be using gradient descent based solution to linear regression. Okay, if time permits, let us see if we could talk about that gradient descent and how you solve this linear regression tomorrow. Otherwise you could go through the lectures also, whichever I have which are available. There also this problem of solving this in another way is discussed. Okay, so maybe I will again take a pause here. Any questions, doubts or any thoughts about it? So this is where you would have realized perhaps the importance of understanding the matrices. The rank of those matrices has something to do with their invertibility and all these things, right? And the way you do all these calculations and you solve a problem, finally how it transforms into dealing with matrices. That is what we have seen in this third part. Okay, I will stop here. Yeah, thank you all.